To speak about inferring user routes and locations using zero permission mobile sensors. The leakage of location information is considered as a major privacy concern. Mobile operating systems like Android and iOS have tried to address this concern by implementing permissions. Though these permissions are successful in mitigating some privacy leakage, there are still apps like the Brightest Flashlight app that deceive users. So this app was sued actually some time back for selling location information without telling the users about that they sell the information. A bigger problem, however, is protecting the leakage of location information from side channels, such as sensors. The reason is that these sensors are not protected by any kind of permissions, nor do they show any notifications to the user about their access. So our goal was to demonstrate the feasibility of using these sensors to infer user routes with a high probability. So this is the outline of our presentation. First, I'll discuss the high-level graph theoretical approach of our attack, followed by the graph construction from the map data. Then I'll discuss the sensors that we use for inference, the challenges with those sensors, and the route construction method from the sensor data. After that, I'll discuss the search algorithm on a high level and report on the evaluation results for both simulation as well as real experiments. So we model this problem as a graph theoretical approach, and we developed some efficient algorithms for search. So basically, over here, an adversary downloads the road network for a large number of areas and converts them to graph where the roads are the vertices and the intersections are the edges. The adversary also creates and distributes an app that detects when a user sits in the car and records the sensor data of the user driving. This sensor data is then processed and converted to a subgraph, which can then be searched in the previously created graph for the maximum likelihood route. So in order to construct our graph, we downloaded the map data from OpenStreetMaps, which is an open source map resource containing the road networks of the major cities. The only place where OpenStreetMaps really lacks is that the speed limit information is incomplete. So we, for that purpose, we use Nokia Here platform. So to construct the graph, the first thing we do is that we decompose each road into one-way atomic sections, where a section is the part of the road between two intersections. So in the example road network shown, those red dots signify the intersections, and the section would be the part of the roads between these intersections. Please note that these sections do not contain any turns or any sharp curves. However, they do contain slight curvature and additional information such as the heading direction and the minimum time. So once we have these atomic sections, we reconstruct them, we connect them together to form longer segments, which are basically either straight or curving roads. So if there are sections that are connected to each other, however, they make an angle of more than 30 degrees, then we label that intersection as a turn, and these sections actually become part of different long segments. So in the example road network over there, S1 is an example of a long segment. S2 north is again a connected long segment. And the figure on the right is the graph that gets generated for our example road network. The sensor data that we use for inference is the gyroscope for extracting turn information and curvature information, the accelerometer for calculating the idle time, and the magnetometer for estimating the heading direction of the car. These sensors on smartphones are generally low cost, and they are extremely prone to noise. So the figure here shows a real experiment route that we conducted, and the corresponding gyroscope and accelerometer drift for that accelerometer trace for that experimental route. So if you look at the gyroscope figure, those sharp deviations are actually the turns recorded by the gyroscope. However, if you see that the y-axis seems to be drifting away from the 0 axis. This is a big problem in gyroscopes. Also, the accelerometer are not suitable for speed estimation because they are very sensitive to the road noises, such as potholes and speed bumps, and like those induce large accelerations, which are very difficult to remove. The magnetometers also are extremely sensitive to the magnets inside the car, and they add a lot of difficulty in estimating the heading direction of the car. So in order to construct the route from the sensor data, we first reduce the gyroscope drift and then align the sensor data to a horizontal reference frame, that is in the reference frame of the car. So what this does is it helps put all the turn information in the z-axis so that it is easier to extract the turn information and the curvature information from one axis itself. So from this z-axis, it is easy to now detect turns as large deviations in the z-axis and extract segments as the trace between two such turns. So for the figure shown below, those red dots signify turn starts or are edges, and those arrows are two examples of segments or the vertices. To each of these segments, we also add additional information, such as like we add the idle time, we remove the idle time information from the accelerometer, and we add compass heading to each segment if they satisfy certain criteria. So once we have the graph and the subgraph, our objective of the search algorithm is to find the sequence of turns in graph that maximize the probability of matching the observed gyroscope turn angles. So if the gyroscope turn angles approximate to a zero mean Gaussian distribution, then maximizing this probability is actually equivalent to minimizing the L2 norm of the errors. So our search algorithm is similar to the trellis code decoding technique, though it has more complications because the start segment is not known. We also get improved results because we filter unlikely or impossible routes at every stage. So we defined two metrics for the search algorithm for evaluation. The individual rank is the rank of the actual exact route in the search results, while the cluster rank is the rank of a group of similar routes that match our actual route. So basically, clustering helps an adversary gain more confidence in an area and target all attacks in the future on that particular area. So this is how the algorithm actually works. First, we assume that every segment or every vertex of a graph is a potential starting point. We iterate through for every intersection, we iterate through every potential path and get the list of all forward connections. Out of these forward connections, the ones that are unlikely or impossible to happen are filtered out, and the remaining connections are scored and added to the previous path score. So basically, now we have these new potential paths with a new score. At the end of every iteration, we just pick the top scoring paths. So basically, this top scoring selection is is a trade-off between speed and inference rate. So if you want better speed, then you can just select a fewer number of paths. If you want more inference, then select more number of paths. We filter out unlikely connections using very flexible thresholds. So for example, if the difference between the reported turn angle and the connection turn angle is less than a certain flexible threshold, then only that connection is selected, otherwise it is rejected. Similarly for time, if there is a particular intersection that is impossible to reach in a given time, then it is rejected. So our scoring is based on weighted turn angles, curvature, and travel time. So basically, we assign a higher weight to curvature and travel time because they are output from the gyroscope, which is a more accurate sensor. We assign a lower weight to time because at any time of the day, the traffic patterns may be unpredictable. The curvature scoring happens by splitting the segment into an equal number of parts as the gyroscope segment that we want to match against. We assume constant velocity for this purpose. However, we see that even with constant velocity, there is a very large increase in the attack performance. Once we have an equal number of segments for the graph vertex as well as the gyroscope vertex, we calculate the curve score as the normalized distance between the segment and the curve for each part. Though L2 norm is theoretically optimal for Gaussian distributions, we preferred the L1 norm over the L2 norm because the L1 norm is much more efficient than the L2 norm, and we observed better results with the L1 norm. So the final score is basically the weighted sum of the turn, travel, time, and curvature score for all the intersections. So we evaluated the gyroscope using error distributions for real driving experiments. So the figure shows the error distributions for 4 smartphones. And as you can see, these distributions approximate to Gaussian distributions, which was our original assumption for choosing the L2 norm. We also observed that 95% of the errors were less than 10 degrees, which is quite ideal for inference. So before I report the simulation results to you, we chose 11 cities for simulation, and they are shown in the table below. So the cities that have a high number of vertices and edges signify the larger cities with a lower potential for inference. Then in the figure, the bottom cities, Rome and Concord, you can see that they have a higher distribution of turns, which signifies that they have a high potential for inference. Then there are cities such as Sunnyvale in the top left, which has mostly 90-degree turns, and that signifies that the inference potential for Sunnyvale may be low. So we create simulation routes by connecting together connected segments of the graph, starting at a random start segment. To simulate real driving scenarios, we injected variable noise to every turn, curve, and time of our simulation route. So there were 4 noise scenarios that we tested against. One was the idle noise scenario, which is the noise-free scenario, and basically serves as the upper bound for performance for our simulation experiments. The typical noise scenario was created using values from real driving experiments and assumed moderate traffic. The high noise scenario assumed heavy traffic on the road and less accurate sensors, while the future scenario assumed moderate traffic and more accurate sensors. Like we think that as MEMS technology progresses, the errors will be less as the sensors will be higher quality. So for simulation routes, we created 2,000 unique routes for each city and tested them against all the 4 noise scenarios. These are the results for 6 of those cities, and this is basically a CDF of the results. So we found good inference for 8 cities where for the typical scenario, we had about 50% of routes in the top 10 results. Even for the high noise scenario, almost 35% of the routes appeared in the top 10 results. For clusters, we basically got 5 to 10% better than the individual ranks. We also observed low inference for grid-like cities such as Manhattan. Another observation that we made was that turn and curvature combined had the largest impact. So if you look at the figures, London and Rome have an equal turn distribution like Boston, Madrid, and Paris. However, London and Rome have a better inference score because they have more curving roads as compared to Boston, Madrid, and Paris, which have more straighter roads. Also, the size of the city doesn't impact inference because London and Rome are the largest cities that we chose for simulations, and they have the best results. We also performed some real driving experiments in Boston and Waltham. So basically, we collected 70 routes each, and our drivers were instructed. So we placed just 2 restrictions on the drivers. One was to have the position of the phone fixed while they were driving, while they were collecting the experiment, and to not reverse during experiment collection. So they were free to keep the phone anywhere inside the car. I mean, there were some experiments which had the phone kept on the coffee holder. There were some with the mount, where the phones were placed on the mount. The key results here were that for Boston, 30% of the routes were found in the top 5 search results, while for Waltham, almost 50% were in the top 5. 13% in Boston ranked 1, while about 38% in Waltham actually ranked 1. Another observation that we made was that the Boston results lean more towards the high noise scenario of simulations, while Waltham results lean more towards the typical noise scenario. This is because of the traffic profile. So basically, Boston has much more congestion than Waltham has, and time has a larger impact in Boston. So to summarize, we demonstrated that apps with no permissions that use these sensors can infer routes with high probability. We modeled this problem as a graph theoretical model to identify the maximum likelihood route. To evaluate our system, we collected 140 driving experiments for Boston and Waltham, and found that 30% of them in Boston were in the top 5, while for Waltham, almost 50% were in the top 5. We also performed simulations for 11 cities and found good inference for 8 cities with more than 50% of routes in top 10. So basically, this suggests that this threat is real and should be mitigated in the future. Thank you.
Brian Rosenberg from Qualcomm. So navigation solutions have a thing called dead reckoning, where they're supposed to be able to estimate the path even in the absence of a GPS signal. Did you derive your kind of segment processing from actual dead reckoning algorithms, or did you investigate?
No, we chose a graph theoretical approach for our. So basically, the problem with dead reckoning is it assumes relatively straighter roads, and it assumes that the accelerometer is actually quite good. I mean, because it depends on speed estimation. In our case, we found that for roads which have speed bumps and potholes, the dead reckoning method doesn't actually work very well. And that's the reason we went for this graph theoretical approach, where we model everything as a graph and then search on it.
Thanks.
Ellie Canal, CMU, very interesting talk. Just on that note, so have you had much success with using signature-based methods to extract all the noise from the accelerometer? You know, like a jolt would be kind of very impulse-driven, whereas a normal turn would look very different.
So we tried filtering on the accelerometer, However, we were not very successful with that because not only are these potholes or speed bumps an issue, even if there are slopes in the road that induce accelerations in the accelerometer, and without the help of other sensors, it is very difficult to remove. So basically, if your car is going down like this, it will actually show up in the accelerometer, and without the help of other sensors, you cannot figure out whether it's the user that actually accelerated the car or whether it's a road slope.
Very good. I'd love to follow up with you on that afterwards. And a second comment more is that taking into account the fact that you're working off the user's phone, it seems the potential that you could use check-ins in Twitter or other location-based areas and then do that as a sanity check to see whether you're actually on the point where the user claims to be might be an interesting way to extend the work. Very nice.
Thank you.
I have to limit it to one more question.
Thanks. Rob Cunningham from MIT Lincoln Lab. I just had a question about your initial conditions. How did you know which city you started in? And can you use some of your techniques to give you a sense of which city you might be in?
Okay, so we perform some tests based on IP address. So if, like when the sensor data gets uploaded to a server, you have the IP address over there. So using the IP address, you can get a good estimate of a particular area a user is in. So in our work, we actually chose cities, but you can extract graphs for larger areas and run the algorithms on those.
Okay.
I hope that answers your question.
All right, let's thank the speaker.